All right, so like I said last time, I want to spend most, if not all of today, doing more practice with the related rate stuff. Any questions on anything we did last time? Or about anything at all, really? All right, let's get back into it. So, new situation for you. So, water tank in the shape of an inverted cone. So, based on the way we attacked these last time, how should we start? What's that? Okay, good. So let's take note of what variables we have. What do we have? We read through what's the first thing. Radius, right? What do you want to call it? R is good. So radius of what exactly? Is the radius of the base of the cone variable? So let's do this. Let's draw a picture. So if I have a circular cone, are we saying that R stands for this length right here? Okay, I think there's no reason to call that to assign that a variable's name. I don't think that value is ever going to change. But what will change? So we're filling this thing up with water. So at any given time, it's going to have some water in it. Let's assume it's not full. So as time goes on, what's the water level going to do? So the water level is going to increase, right? So what else is going to increase as the water level increases? The what? Right. So I think radius is a good variable, but I think let's call this value right here the radius. We'll call this R. And this one right here we know is 2 meters. That won't change. So I'm going to say the radius of the water surface at time t. And that is being measured in meters. So we also just implied time there. So time elapsed. In what unit is time measured in this time? Minutes. All right, so we got 2 variables. What else should we talk about? The height of what specifically? There we go. So same idea there. It's not really worthwhile to talk about the height of this tank because that doesn't vary. So I'll call this length right here H. So H is the water level at time t. That's also going to be measured in meters. All right, anything else? And there's one more quantity here, not even talking about the rates that we can get by joining these quantities together. I think there's one more quantity where we have to think about in order to do this. So the rate the water is filling. So let's talk about that rate. So the rate at which the water level is rising, or is that the one you're talking about? Okay. So the rate at which the water level is rising, what do we call that rate? vote for dr dt. What variable did we assign to the water level here? H. So it should be dh dt. So this is the rate at which water level is rising. And what's a good unit for that rate? Meters per minute? Not cubed. So we're looking at the water level, right? The water level, okay. That's a line. What idea are you thinking about? So that was the last quantity I think we need to look at. So the V is the volume of water in tank at time t. That'll be cubic meters. All right. Anything else we should set aside? We'll come back and revisit that if we need to. That's a good place to get started. So we got a bunch of variables written down. We've got a picture of our situation here. We know what this tank looks like. What do you want to do now? Okay, so based on the things that are here, I really should have an equation for the volume of the cone. Do we remember what that is? Yep. Some of you have probably seen the demonstration where if you have a cylinder of a certain height and radius and a cone of the same height and radius, you can fill up the cone 3 times. All right, so there is that's a good equation. In fact, let's not clutter this up too much. So I got V equals 1/3 pi r squared H. Definitely need that. All right, what else can we, where should we go from having that equation? Sebastian? You see it on there? So that 2 meters cubed per minute, think about what that is describing. And based on what it's describing, ddt. Yeah, that was the maybe not the only one I thought we were missing, but it was a crucial one. So dv dt, what can I call that? How was it described up here? I'm gonna call that I'll call it the flow rate. Flow rate of water into tank. And that is given to us in cubic meters per minute. I think there are other rates we could talk about. I don't know if they're going to be important. So right now, we'll go with this. So we have the rate of change of V with respect to time, the rate of change of height with respect to time. We don't have drdt, but maybe we will. If we need it, we'll add it. If we don't, then we'll keep going. So now that I think my variable list is stronger now. It's better now. I have this equation for volume. It's a function of radius and height. What can I do now with that equation? Sebastian? I can plug in the radius. I don't think, do I know the radius? I don't think so. And that's, keep in mind, when we said what R stood for, R stands for the radius of that water surface. So, what am I trying to do? What thing am I trying to solve? Pardon, what? Trying to find DHDT. What tells you that? Right. So the rate at which the water level is rising. So of all these things, I know I'm looking for DHDT. That's the thing I want to solve out of all this. So if that's the thing I want to solve, where does time appear in this, in the only equation? We have to do something to involve time in how we're looking at this cone. The derivative with respect to what variable? With what? That's going to be with respect to time. So I mean, when we do chain rule, we're going to have to basically take these derivatives in layers. But for right now, we're just taking, yeah, we're going to take the derivative with respect to time. So left-hand side becomes dv dt, which, as we just said, is something we know for sure. All right, and what are we going to have to do to handle that derivative on the right-hand side, the 1/3 pi r squared h? I heard a vote for product rules. We agree the product rules needed here? Why do we have to use product rule? You got two different variables, which you can't really help but treat them as different functions. So off to the side here, I'm going to say that u is equal to 1/3 pi r squared, and v is equal to h. What's the derivative of u with respect to time? Q3 pi r dr dt. We agree with that. That's a good question. Where did dr dt come from? Right. So you're taking the derivative of, so this u here, u is a function of r. But r is a function of t. So really you have this composed function thing going on. T governs, so the time governs the radius of the water level. And the radius of the water level governs, well, what this function u that we pulled apart, this 1/3 pi r squared, which is part of the volume, but not all of it. So think about the way chain rule works. The first thing I have to do is take the derivative of u with respect to r. That gives me 1/3 pi, yeah, that gives me 2/3 pi r. Then the chain rule says I'd take the derivative of r with respect to t. Which are the only thing I know. The only thing I know to do with that is dr dt. All right, and then what's dv dt equal to? 1. Is that all? Yeah, so basically, even though it's not as obvious there, that's the chain rule again, because v is a function of h, but h is a function of t. So the derivative of h with respect to h is just 1. But then that inner layer, that's where the dh dt comes from. So we have all the pieces of product rule. Let's go ahead and put them together. I think I get 1/3 pi r squared dh dt plus 2/3 pi r h dr dt. That was product rule because basically, so this first term on the left here. Do I have enough information to solve the thing I want to solve? So here's the thing I want. Do I have dv dt? Do I have r? Okay, so I could, but right now we recognize that you don't. Do I have h? I think I have h. Do I have dr dt? No, but I can probably get there. All right, so I don't know the radius, but I think I do have enough information to find out what the radius is. Because let's just take a cross section here. If I make a right triangle out of this, back. If I make a right triangle out of this, what did I say the height was? 4. And the radius is 2. So that 2-meter radius and the 4-meter height, that's for the whole conical tank, right? But if I just have, really what I just have is this situation. The tank is partially full of water. Would we agree that the triangle that's nested inside the bigger triangle, those things are similar? Okay. And since they're similar, then I can make this conclusion. If I have this triangle, whose height is 3 meters, can I get the radius from there? What's that radius? $1.5? Right, I agree with that. Yeah, let's unpack that. How do we get 1.5 meters there? So since I know these triangles are similar, I know that 4 times some some scaling number, some scaling factor is 3. So that gives me that x equals 3/4, right? So how did I use that 3/4 to get to my other measurement? Yeah, just multiply 2 times that scale factor to get that other corresponding length that I want. All right, so we got R. We still have this dr dt thing here. Can we do anything about that? I'm gonna erase this to give myself some more space. Is there anything we can do with dr dt? Yeah, I mean, a similar triangle can bias that too. So I really, and that's kind of tricky. I know we spent a lot of time on this one, but I think it deserves it. Let's do this a couple different ways. So we have this similar triangle idea now, which I hadn't erased it, but what can we say about the heights? How is the height related to the radius at any time? So this triangle I just had here was, so this time I'm not looking across triangles. So we just had this one for a 3 meter high water level and 1.5 meters was the radius, right? How is the height and the radius? How are the height and radius related? Radius is half the height, right? So I can say this: the radius is equal to, and I'll say it this way: h is equal to 2r, right? Then would you say this is true? dh dt is equal to 2 dr dt. Well, r is the same r from. R. I can take a derivative of both sides and say that, all right, the rate of change of the height with respect to time will always be double the rate of change of the radius with respect to time. Go ahead.
In general, it was about radius and the height of
Oh, yeah. Right. From the fact that phones have that slant side is straight. Yeah, this is really the shape of them. We have no local relating them. All right, so if we're okay with that, I'm going to rewrite this equation. So dv dt equals 1/3 pi r squared. And I want to solve for dh dt, right? dh dt plus 2/3 pi r h times 1/2 dh dt. We okay with that? Basically, what I did here was solve this thing for dr dt. So dr dt equals 1/2 dh dt. You're okay with that? We're very near the end where we can start plugging in numbers. get what we asked for. But I want to make sure everyone's written down the things they want to write down, and you've gotten all your questions answered that you want answered. All right, so dVdt is going to be equal to 2, correct? Times 1/3 pi times 1 point, oh, not 0.15. 1.5 squared times dH/dt plus 1/3 pi times 3 times 1.5 times dH/dt. I combined the 1/2 and the 2/3. That's why it's now 1/3. Just combine it in any convenient, happy way. Oh no, there's a one. This is a 1.5. Back out of dH/dt for now. 1/3 pi times 2.25 plus 1/3 pi times 4.5. Someone wants to do that for us, that's great. But the good news is is that I'm going to put it down until someone refutes it. Just for a sec. Now that we've done this, there's a lot of stuff going on here. I didn't really have enough room to capture everything. First of all, any questions about the way we did this? Go ahead. No, that's not arbitrary. 1.5. What? I mean, the bad news about this example and I guess the simple ones that you don't recognize like similar shapes or so that's gonna be something crucial. And I think your best chance of being able to realize that is drawing. I didn't draw that many pictures for a few, but draw out whenever you need to. And another thing I want to call back to. This is the first time we've had to think about similar geometric shapes, but that's a pretty common thread that you'll run into for these. Any other questions about how we got here? Can I take a chance at making you even more angry? So this is obviously pretty nasty, right? So I'm going to back up. I want to duplicate this slide. And just show you one thing to think about. We're not going to rework this example again, but there's one thing I want to think about. So we ran into a lot of problems trying to deal with that derivative in terms of with the radius and the height and related to each other, right? So here's something that would make this a lot more efficient. So we said this was the volume of the cone, right? Specifically the cone shaped like water inside the tank. We said this at some point, right? That H is equal to 2R. Oh, man. So if the height is equal to 2R, think about how this would have gone if I would have substituted that in before I started doing a bunch of calculus. Two-thirds pi r cubed. So think about the derivative that we had to deal with. We had to deal with product rule, which got a little more complicated. We had to, so one thing to keep in mind, this H equals 2R. I didn't get around with there's no way to get to the end of this. Picking up on the fact that you can deal with similar triangles. But the moral of the story here is if there is some simplifications you can do like upstream of the calculus before you start taking derivatives, it's usually going to save you a lot of time. I mean, this derivative comes out to be what? 3 pi r squared drdt. And I'm realizing I should have subbed in for R, not for H, but that comes from this idea of the similar triangles. So I'll direct your attention to the one that's not no matter how anything else about this thing? All right, before I probably just do one more example today, but I want to talk about this. Is there a process that we've kind of stuck to organize this and lay this out? What have we done? So define variables. I'm going to say this carefully because I think the temptation I've seen in the past, and I saw a little bit. And I don't think it was until we were able to get the actual thing we want. So be as specific as you need to be. So define the variables. Yeah, so identify the variable we are solving for. So write equation. I'll say equations because in this last example, no matter, like I showed you 2 different ways we could have attacked it, really needed 2 equations working together to get that done. After we write that equation, what do we usually do with it? I don't think that, I think something must come before plugging stuff in. Not only can you take the derivative, I would say you must do that. Take derivative, usually with respect to what variable? I think exclusively in the ones we've looked at, they've all been with respect to the same variable. So substitute known values, and then once you've done that, yeah, then you can solve. There's one step I might add here that I would strongly encourage, and that was the draw the situation. Doesn't have to look good. None of my drawings look good, but they just have to kind of organize. You're looking at that. Anything else on this? Any more detail? All right, I got 2 more examples. I think we're just going to stick with one. This is a good one. All right. So car A is traveling west. Car B is traveling north. There's a car. The car doesn't have to look good. So car A and car B. They're traveling in these directions. All right, I know something about speeds. Oh, I think my picture is messed up, isn't it? Yeah, they are. So let's say they're going to meet here. See, now I'm getting tripped up. That means A is here, right? And B is here. A is traveling west towards it. B is traveling north towards that X. Okay, now I feel better. Okay. All right, so I got according to you all, variables are next. Variables to think about. The distance between the car and the intersection. So we're going to need two things to capture that, right? What are some good? So I want to count one variable that captures the distance of car A from the intersection, one variable that captures the distance of car B from the intersection. What should I call those variables? A and B are fine. So A and B are going to be distances from car to intersection. And how do we want to, what's the unit we want to use for that? Miles. Okay, so I'm going to label this A. I'm going to label this little b. What else? So why do I need the distance between the cars themselves? What clues you into that? Right. So I'm looking for how, I'm not looking for how car A is approaching the intersection or how car B is approaching the intersection. I'm looking for how fast they're coming to each other. That tells me a new distance. What should we call that distance? Why not? So C is the distance from, more efficient way to say this, between cars. Also in miles. Any other variables we should look at? So yeah, I think dAdt, dVdt, and dCdt. Are we okay if I leave off the language of what they'll stand for? Let me have one of you verbalize it. So let's say, what does dVdt signify? What does that represent? Velocity of car B. We okay with that? So I have the velocity of car B and the rate of change of the distance between car B and the intersection. Are those two things, obviously they sound different. Are they similar? Are they equivalent? I think based on what we want to do, they're going to be. You can think of those things. Those are both great definitions for what dVdt is. All right. I think we got a good handle on variables. We're sorry. Do we need C? I'm going to vote for yes. What's the key language? Tell me what's the underline here that tells us that I care about C at all. Each other. So at what rate are the cars approaching each other? So yeah, we do need C. All right, I think we're good on the diagram and the variables. So where do we go from here? Pythagorean theorem. So that literally the way we named the variables, we just write it down like we were in. How do we know we can use the Pythagorean theorem? Not just, oh, it's a right triangle. Yeah, it needs to be a right triangle, which it is, right? North and west are perpendicular directions. All right, so we have this equation. What do I do with it? Take the derivative with respect to time. What's the left-hand side become? ADT. VDVDT. And equals. Very good. All right, and which one of these things do I care to solve for? Right, so I don't think we identified that early, but that's okay. The steps are, it's not like you can't revisit past steps. So I want dc dt, which means I better know the rest. So I have 1, 2, 3, 4, 5, 6 variables. I better know what 5 of them are. Do I know what a is? Ooh, is a 50? So I'm glad that came up. Keep in mind what a stands for. A stands for a distance, right? So I have a. Do I have dA dt? Do I have b and dv dt? Do I have c? I can get it. I don't have it, but I can get it. So a is 0.3 miles, right? dA dt is what? 50. B is 0.4. dv dt is going to be 60 miles per hour. Equals 2 times, what is c? How did you do that? Right. So Pythagorean theorem is still going to help us because if I know both the distances on the legs of this triangle, 0.3 squared plus 0.4 squared equals, I believe, 0.25, which is equal to 0.5. So yeah, I think we have enough here. Would it please the court if I just did this, cancel 2 out of everything? Divide the entire equation by 2. So then I get 1.5 plus 2.4 equals 0.5 times dc dt. I feel like I made a mistake. 15 and 24, huh? All right. And I believe that comes out to this rate of change being 78 miles per hour. 7.8 makes no sense. All right. We feel a little bit better. 48 hours. So I opened this thing on WebWorks last time. You can point on me, right? Any questions before we go? Yeah. Oh. Myself with the quiz with that